Thank you. We have very quickly covered the essential aspects of a BJT in a bipolar IC environment. But this MOSFET I could not discuss. Now I want to discuss a little bit about the MOSFET IC. Let us draw the structure of a MOS IC, which have already been discussed in some previous classes. So this one is a structure of an N-channel MOSFET. Which basically consists of a p-type substrate, and as before, by BJT also you remember the substrate was p-type. The concentration of this substrate is typically around 10 to the power 16 holes per centimeter cube, typically around. For the dopants, usually is boron doped silicon. The substrate is a boron doped silicon wafer with a doping concentration of the order of 10 to the power 16 per centimeter cube. Here, at least apparently, it shows that we find the structure is much simpler than that of a bipolar transistor. There are two diffusions, as somebody was pointing out in the beginning. So far as the technology is concerned, it is simpler. There are two diffusions, and today, of course, it is substituted by ion implantation. Okay, and then the only crucial aspect of MOS is that in the region between the source and drain, these are called source diffusion and drain diffusion. This region, over this region, there is an ultra thin, high quality silicon dioxide film. This ultra thin silicon dioxide film extending from source to drain is called gate oxide. This one is called gate oxide. Whereas the remaining region is covered by a thick oxide called field oxide. This is very thin, and this is thick. This is of course very relative, isn't it? Very thin and thick, the words are very relative words. Qualitatively okay, but quantitatively, let me tell you that this LSI and VLSI MOSFETs, if I called in this thickness as T oxide, oxide thickness, and the other is T field, oxide thickness in LSI was around 1000 angstrom, and this is around 300 angstrom today. Of course, in discharge stage it has gone even below 100 angstrom. This was around 1 micron, means 10,000 angstrom. It has come to the level of 3000 angstrom today. So this is very important to note that this oxide from the source to drain region called channel region, this region is also called channel, okay, is very thin and is of very, very high quality. And the remaining region, most of the other space, it is covered by thick oxide. It was around 10,000 angstrom in the LSI era, whereas today's VLSI era, its thickness is around 3,000, sometimes to 5,000, usually around 3,000 angstrom. Okay. Then there are three ohmic contacts. You see that one, and this one. This is the ohmic contact from the source diffusion. This is the ohmic contact from the substrate, and this is the ohmic contact from drain. And you have seen that in this particular diagram, I have shown that the source and substrate are short-circuited, and this is what is normally done. Otherwise, this MOSFET is a bilaterally symmetric device. If I do not short-circuit this one here, if I short-circuit, it becomes asymmetric after fabrication. But otherwise, you see that you can interchange source and drain, which you cannot in BJT. In BJT, you cannot interchange emitter and collector. What is going to happen if I interchange emitter and collector? Any one of you? And just one. One of you please answer.
Beta comes down drastically.
Beta comes down drastically. Yes. So therefore, you've seen because of the high amps asymmetry involved in the bipolar structure, may not be true for the lateral PNP transistor. But still it is true that if you go into the details of structure, you'll find even lateral PNP transistor also is not symmetric. I've shown you the cross section. That is why it appeared as symmetric. But if I see the bar side, the plan, it is highly asymmetric. But in MOSFETs are totally bilaterally symmetric, and this is an advantageous feature of MOSFET while designing a MOS circuit. Okay. Then I told you that this region, there is an ultra thin oxide. It was a technologically crucial thing. I have mentioned in the last class that though the theory of MOSFET was almost, it was known quite earlier, almost the same time when bipolar junction transistor was invented. But the first successful, commercially successful MOSFET came in 60. Because, why? This problem. A very, very stable, good, high quality thermal oxide in the gate region. This was a crucial thing. Always this oxide was found to be leaky and many, many problems were there. And what is the typical gate resistance today in a MOSFET? Maybe hundreds of mega ohm. Why? Simply because that this oxide has an effective, though it is thin as 300 angstrom. And you will wonder to know that people are now making MOSFETs with around 100 angstrom gate oxide. But even if it is 100 angstrom, the resistivity of this film is around 10 to the 15 to 10 to the 16 ohm centimeter. Gate oxide resistivity is a very important term. Gate oxide resistivity around 10 to the power 15 to 10 to the 16 ohm centimeter. Whereas the breakdown voltage or the breakdown strength these two are very important things. One has to achieve very high resistivity so that the input impedance resistance is very, very high. And that's the main important thing of MOSFET. No? You can store charge. And second is the breakdown strength has to be also very high, because otherwise if thickness is so small, a low voltage will break down, so this is not desirable. And the third thing, any one of you, what is the third important requirement for a good MOSFET? The interface, silicon and silicon dioxide, should be excellent. It should have a very, very low interface state density. The interface state density in the, you remember that, the interface state density should be extremely low, less than 10 to the power 10 parts centimeter square per electron volt. The interface state density, it is called QIT. QI interface trap is of the order of or even less than 10 to the power 10 per centimeter square per electron volt. And another parameter is also very important. The fixed oxide charge should be of the order again 10 to the power 10 per into Q per centimeter square, coulomb per centimeter square. Q means electronic charge. You remember that some device physics was discussed in quite a long time ago. And remember, these are some of the very important features which must be maintained. One is the interface state trap density. The other is fixed oxide charge density in the gate oxide interface. This thing quantity should be controlled precisely. Otherwise, you are not going to have a success, very satisfactory MOSFET. Though structurally MOSFET is so simple compared to a BJT, it took some good amount of time for commercializing this product. But once the success achieved, you remember the tremendous growth. From the simple LSI to, I told you the 60s and 70s and 80s were almost totally 50s were bipolar era. 60s were partly bipolar and partly MOS era. And 70s were almost 100% MOS era. There was a rapid transformation of technology, innovation of technology from PMOS to NMOS, NMOS to CMOS, then miniaturization, and you have seen how the different chips have come, Intel 486, 386, 480, now Pentium, and many things have come. The memory technology is fantastic. even it is now possible to have a 64 megabit DRAM, or people are, that some people I think have announced that 1 gigabit DRAM. The technological status of these things have really changed fantastically during the last 15 to 20 years. And that's the status, okay? But everything is around the MOS, mostly around MOS, CMOS. CMOS is the latest one. Now here, again, when you compare with bipolar, what are the, can you suggest, tell me what are the differences? One, structure is simple, but crucial thing is the oxide, I told you. What are the other things? Bilaterally symmetric is good. For design purpose, layout design purpose is very good. Anything else? Have you seen that isolation kind of things here? It is not shown. That P plus isolation, N-type, epitaxial. Where is that epitaxial film gone? Is it necessary? Is it essential? No. Today, only in the very advanced CMOS technology, it has started using epitaxial film. But otherwise, there is no need. Epitaxial is a very complicated technology. Of all processes which I have discussed, epitaxy is the most difficult one. So that is not there. It is bilaterally symmetric. And there is no isolation, so-called P plus and all these things. Then there is a need for isolation. How it is achieved here? How it is achieved? Automatic, because these are all N plus in P. So N plus things are floating in P type C. And what is the polarity of bias at the drain? You see the source and substrate is usually short-shorted for all the transistors. But what is the bias at the drain? In this case, positive or negative? Positive with this positive. So, and if the ground is kept ground, then is the substrate is kept grounded, then this junction is reverse bias. So all the drains are reverse bias junctions. These are silicon ones, and they can be very small size, of very small size. So leakage resistance and capacitance both are very small. And there is no need of extra isolation and all these space sacrificing things. You know that automatically there is an advantage. Can you tell me any other advantage from IC point of view? That is, I think all of you know that. There is no need of resistors. As you remember, in a bipolar circuit, either you consider linear circuits like op-amp or a digital circuit like TTL gates. What are the components? Transistors and resistors, and some diodes in certain cases. But in MOS IC, you know something about MOS IC. Is there any resistor external? No. You know that the switch or even the CMOS linear circuits which were coming up, both the devices, that means the driver and load, the pull down and pull up, both can be achieved by using a MOSFET. In such a case, the load is usually called an active load. In bipolar circuits, the loads are usually passive loads, mean normal resistors are used. But in MOS circuits, particularly in digital MOS circuits, there is no need of using passive resistors as load. You can use MOSFETs themselves as loads. Advantage? I mentioned in the last class that resistors occupy a large area for various reasons. We shall discuss that but in a little bit more detail afterward. Resistors lay a lot of area, and if they suffer from temperature, coefficient of resistance, all these other problems. In this case, you simply can realize so-called a load by, again, another MOSFET, and the overall space saving is fantastic. Fantastic. Suppose you wanted to use a passive resistor in a MOS circuitry, what we have to do? Can anyone of you tell me? Suppose I'm not satisfied with a nonlinear resistor. After all, a MOSFET resistor, a resistor realized by a MOSFET, cannot be a ohmic resistor. I versus V relationship will not be a good linear relation. It will be nonlinear. But I am not satisfied with that. I want to have standard good resistors which are linear in nature in a MOS circuit. What do I have to do? Again, I am in problem because the resistors cannot float, cannot be just done like this. I have to float, I have to have some isolation. Either you have an N plus region into which you may have a P, and that P may behave as a resistor. And that way you are going to, because you need an isolation, extra isolation, you are going to sacrifice a lot of space. Your packing density is going to, so therefore, it is not a good idea to have normal linear resistors into a MOS circuit. But for your information, very advanced MOS ramps today are using passive resistors. But these passive resistors are used by polysilicon, not by other techniques. We shall discuss that afterward. What are the advantages of polysilicon resistors compared to other resistors? We shall discuss afterward. But for your information, it is not true that all MOS circuits do not use any passive resistor. It is not true today. Today, certain very specific MOS ramps are using passive resistors, but passive resistors are loads, but these passive resistors are realized from polysilicon film on oxide. We shall discuss that afterward. Okay? So you see that if you now combine all these features, you are finding that you are definitely on the very much on the positive side so far as a realization of the realization of an IC is concerned. IC means I always need a high packing density, more functionality, more complexity, low power dissipation, higher speed, etc., etc. But are you satisfied with all of them now at this moment? If you have some idea about bipolar and MOSFETs, are you satisfied in all ways while having MOSFETs? In what ways you are not satisfied?
Speed is less.
Speed is less. Can you just give some specific examples? Speed is less is a very qualitative one, isn't it? Can you be more specific? You compare TTL with, say, NMOS. Do you think that TTL is speedier than NMOS? What kind of TTL? Schottky TTL. Yes. Schottky TTL is speedier than NMOS, but I know that here when we compare, we normally compare with, we assume that the minimum feature size is the same in both ICs. Have to be kept in mind. These are all relative comparison. If I assume that 3 micron is the minimum feature size in both bipolar circuits and MOSFET circuits, then comparing a TTL and bipolar, then speed-wise, bipolar is much better, no doubt of it. Let me repeat. If we assume that both bipolar and MOS circuits under comparison have the same minimum feature size, for example 3 micron, then bipolar circuits, particularly TTL and Schottky TTL, will have a higher speed compared to NMOS. But NMOS will have little edge so far as power consumption is concerned. Okay? But you know that what is the highest speed version of all logic families? ECL. Why? Why? Because unsaturated logic, we don't allow the transistor to saturate. Therefore, the storage time concept is not there and overall speed is very high. But what is the drawback? High power. So ECL is very good, but again, let me quote you some practical figures. A advanced ECL logic today, advanced means commercially available product. I am speaking of all commercial available products. Will have a internal propagation delay of 1 to 1.5 nanosecond. On the other hand, you can have CMOS today. Otherwise, you could not have those mini and all these things, that fantastic high-speed ones. But today's even CMOS is offering you speed as much less than a nanosecond, much less than a nanosecond. Because in CMOS technology, the packing density and all these things have been so much improved. So, and speed power point product point of view, that is power delay product of point of view, nobody can beat CMOS at this moment. But even from speed point of view, one can have now CMOS, which is speedier than ECL. Again, please keep in mind, in the two comparisons, the minimum feature size is not the same. If you can bring down, if you can reduce the size of ECL to those submicron features as CMOS have done, you can get a higher speed. But technologically, from various points of view, it is difficult. Because after all, you know, the bipolar is a multi-layer structures. It's very difficult to have very small size in bipolar transistors. MOSFETs basically simpler. Therefore, you know, state is presented. If anybody asks you about this, that which one is better and all this thing, you have to keep in mind something is kept to be constant. Assume that, yeah, normally we say if in textbook we find that MOSFETs are speedier, bipolar transistors are higher speed than MOSFETs. Or in certain other textbook, they say that no, it is unipolar. So MOSFETs are highest are speedier, and you know you'll find variations various, but these things should be very clear to you that if you consider the minimum feature size the constant same in both technologies, ECL is the speediest. But MOS technology have been developed to a great extent. The feature size has been reduced to even deep submicron today, and that's why MOS is giving you all better features than bipolar, and that's the thing. So the advantage, one of the advantages you should mention, so if you summarize the MOSFET compared to bipolar, you find, number one, MOSFET structures are bilaterally symmetric, lot of advantage in design. Bilateral symmetry of MOS circuitry or MOS devices. Number two, self-isolation. This is what is called, MOSFETs are self-isolated. And number three is the very high input resistance, which offers the advantage of dynamic logic realization. Very, very high input resistance of the order of tens to hundreds of mega ohms offers you the advantage of dynamic logic implementation. Then it is very compatible with VLSI technology, very, very compatible with VLSI technology, with a very high packing density, because MOSFETs can be used both as drivers and loads. So the driver load combination of MOSFETs, another very interesting feature, which makes MOSFET naturally advantageous so far as VLSI realization is concerned. And is there any other point left out? Power. It is intrinsically consuming low power, and the CMOS technology is the lowest power version of all VLSI logic families, including I2L. CMOS, the combination of NMOS and PMOS, the complementary symmetry MOS technology offers you the lowest power of all logic families, including I2L. So you should be very happy with MOS, isn't it? Why should you unnecessarily consider bipolar at all for your future? All bipolar activities should stop. Am I correct? But has it stopped? No. That must be some positive features with bipolar. What are the positive features with bipolar? It can. I think you should answer. You should answer one by one. Okay. What if any one of you want to answer, please. What is the what you said about power? What did you say about power? Any one of you, please.
It's good for power devices. Can handle more power than.
Can handle more power. Okay. Any other feature?
Bipolar transistors are better for analog function.
Yeah, it's a very important thing. It has been found that MOSFETs can also be used. Today is also being used for analog devices. But naturally, there are certain other, it has been found after the overall integration. By integration, I mean that considering all aspects and from experimental experience, that bipolars have added advantages for analog circuit realization. And hence, one is more power handling capability, as rightly said by one of you, and then the second one is the analog signal processing capability, better analog signal processing capability of bipolar ICs. And therefore, I have mentioned in the last class that people are now combining the two technologies. People are now producing chips combining both bipolar transistors and MOSFETs, particularly CMOS, and they have come up with a technology known as BiMOS, or today it is called BiCMOS. The most people know BiCMOS is a very, very important process today, technology BiCMOS. And number of conferences are held on BiCMOS technologies. And can you tell me that why you unnecessarily, the technology will be very complicated. Implementing both bipolar transistors and MOSFETs on the same chip, where both kinds of devices should have very good features, high performance. That is needed. Otherwise, if you want to integrate bipolar in MOSFET, and that as a result, MOSFETs are much inferior to bipolars, or vice versa, it will be very bad. You have to take some route so that ultimately both kinds of devices are very excellent in their performance. A good BiCMOS, but in that case, definitely your technology is going to be more complicated. You can't deny it. But why are you doing that unnecessarily? Could you not try to modernize or try to innovate something in the MOS so that even MOS become powerful for handling, for doing analog signal processing and for handling power, more power. Yes, that is also being tried upon. People are not just sitting idly. Pure MOS technologies, they have been successful to a great extent to improve the power handling capability of MOSFETs and to come up with excellent analog functional capability of MOSFETs also. But again, from design point of view, bipolar is simpler. From design, and it has been found that if I can combine the two efficiently, there are a lot of advantages. Then why unnecessarily you are introducing analog functions also into the same chip? Is it necessary today? Is it necessary today? Because today I find that everything, world is being digital. Is it at all necessary to have analog functions to be implemented on a chip? Unfortunately, yes, because particularly in applications like, say, biomedical, automation, and all these things, the basic signal which the nature generates, say temperature in a furnace or say gas blind, etc. And similarly, our ECG signal and all these things, they are basically analog in nature. And you have to do something. That means first you have to need an amplification of that analog signal, and then AD conversion and all these things. And ultimately, again, in most applications, I want to get back the analog signal. For example, in radio, you want to get the original modulating signal. Okay, Similarly, here also in many applications we want to get back the original signal, but in a different version, and in a very high power. Therefore, it is wise to combine the two technologies, but debates are going on. BiCMOS initially produced a lot of enthusiasm to the scientist, but gradually it is found that again CMOS is taking up so quickly everything, all aspects. CMOS, CMOS powers and many power modules, power cards are being produced by using CMOS technology or NMOS technology. And analog signal also, I have heard of micro power op amps. Have you heard of any one of you? Particularly used in pacemakers and in other applications, implantable devices. Micro power op amps, they are realized using CMOS technology. So things are going very fast, but there is potential definitely. At this moment, one can say that yes, BiCMOS also has got a good amount of potential. Thank you. Now, before I close today, I'll just quickly discuss about the different techniques today which are used in isolation of devices in an IC. I told you about junction isolation, and MOSFETs are also junction isolated, but there is no need of separate junction isolation. But this junction isolation, what is the main problem? Leakage current is extremely small. One can in the technology, because sizes are so small and silicon is a very good material, its band gap is wider, and leakage current point of view, it is not that disadvantageous. More problem arises from the capacitances. Even if you reverse bias it, the capacitance of the reverse bias junction, may be sufficiently reactive. That reactance of capacitance is 1 upon omega c. As omega increases, that reactance decreases. So above a certain frequency, even a small capacitance appears to be almost a short circuit. And today, what is the trend? Even a PC today has got a clock frequency of 65 megahertz. Even a PC 486 today is equipped with a clock of 65 megahertz. Ordinary mini computer is a good frame. I'm not speaking of the mainframes. Mainframe, by today's mainframe, we mean this so-called supercomputer, which has got gigabit rate clocks. But ordinary, so-called minis which are coming, the various workstation formats, they have clocks around 100 megahertz or even more than that. So you know that these frequencies are quite high, and the kind of isolation which is needed cannot be achieved by junction isolation. Junction isolation is not sufficient to do that. So I have to find out certain other alternatives for that. So what people do, let me just show you one thing. As I told you that, suppose, say bipolar technology, let us consider it that only. So this is a situation. I have shown you a number of N-type islands which are floating in a P-type substrate, all surrounded by P+. And I say that these islands, N-type wells, are electrically isolated from each other. I have shown a number, 1, 2, 3, 4 such islands. in the plane of the paper. Similarly, there will be such islands perpendicular also to the plane of the figure. Okay. Now, you remember the junction capacitance formula for the simple case of step junction. And according to that, I think you will remember the depletion layer weight is inversely proportional to the square root of doping. For a step junction or abrupt junction, the depletion layer weight is inversely proportional to the square root of the doping concentration. And therefore, if we draw the depletion layer, say for example around these structures, if we draw some depletion layers, so it will be something like this. This green boundary with shades indicate depletion layer weights, depletion layer regions around an N-type island in this cross section. You note that near the surface the depletion layer weight is extremely small, whereas near the bottom it is the maximum. Why? Here the depletion layer weight is very small, but here it is large. Why? Yeah, because this was done by isolation diffusion. You remember, by a photolithographic step on the N-type layer, I etched windows here, 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 and then had a doping of boron, very heavy concentration doping of boron through these windows, so that ultimately we get continuous p-type region here, here, here. All the N islands are surrounded by p. Ultimately we get that. You remember the technique. So near the surface, boron concentration is very high compared to the near the in the bulk, in the depths. So the depletion layer width, as according to our that depletion layer is inversely proportional to the square root of doping, it should be minimum near the surface and maximum near the bottom. And what about capacitance or capacitance per unit area of junction? That should be maximum therefore near the surface and minimum near the bottom. Am I correct? And it can be shown that it is this sidewall component that is called, then therefore structurally we can divide the capacitance around an island into two. One is the capacitance of the sidewalls and the capacitance of the bottom. It can be shown that it is the sidewall component of the capacitance which play a very important role in electrostatic coupling between the islands to produce the so-called electrostatic leakage, capacitive leakage. By electrostatic I mean capacitive leakage. Because the capacitance of the diffusion, the sidewalls will be much more than the capacitance of the bottom portion. So can I do now something to improve upon it? What people do is as follows. They cover it by an oxide first, and they do some, I will not go into the details of technology in this course because it will be unnecessarily taking time. By a very special technique, they first remove from this region about 50% of silicon, etch off. By using a photolithographic technique, they etch off from the P plus regions about 50% of silicon. By 50% I mean 50% of the epi layer. So up to this it is removed. Do you follow what I have stated? I remove silicon from this region from this region, and this region. Ultimately, this silicon surface here is 50%, that is half of the epi layer thickness. Then I carry on a wet oxidation or certain oxidation process by covering this region. That is, these regions are kept covered. The island regions are all covered by a nitride film, silicon nitride film. Technique is such that all the island regions are covered by silicon nitride films, whereas these regions silicon is little bit etched. About 50% of the epi layer silicon has been removed. I grow silicon dioxide by wet oxidation technique. By wet oxidation I mean by treating the silicon wafers in oxygen plus water vapor atmosphere at a temperature around 1100 degrees centigrade. At a temperature around 1100 degrees centigrade with oxygen plus water vapor. It's called wet oxidation environment. And what will happen? Silicon will be oxidized, this silicon will be oxidized, but nitride has got a very low oxidation rate. So nitride will not practically be oxidized. Only the silicon here in these regions will be oxidized. Now, as silicon is oxidized, means it is not an oxide deposition. This is an oxidation. Please remember, silicon reacts with oxygen to produce silicon dioxide. It is not an additional oxide film. So what will happen as a result? As oxidation goes on, this silicon interface will gradually go down because the oxide has got a volume density which is twice that of silicon. Silicon dioxide's density is almost half of that. Silicon has got it. So volume density that I have said, silicon density is roughly 50% of silicon dioxide. So what will happen? There will be a volume expansion. Silicon dioxide, as silicon gets converted into silicon dioxide, its volume will also be expanded doubly. So what will happen as a result? Ultimately, after some time, this whole region will be converted into silicon dioxide. And this interface, original silicon interface, will now come here. I think you understand that. Why silicon interface will go down? Because the volume expansion which will take place after oxidation. It is roughly twice.
It will enter into the island area also.
Yeah, there will be little, and that is why I'm saying that in detail, if I go, I don't think we have much time in hand, but I'm showing at the end of a typical age, I'm trying to show what will happen. It will look like this. This one is your nitride. The blue one is nitride. Si3N4. And this is your N-type silicon region. And this is your silicon dioxide. Normally below the nitride there is a very thin oxide film kept, at which I have not. I'm not discussing the details of technology. Actually, what is done in nitride, this process, initially you have a very thin oxide film deposited and then grown, and then thereafter you deposit a nitride film. and then do that oxidation. What will happen? As a result, there will be lateral oxidation. Not only oxidation will take place vertically there, and ultimately, as rightly pointed out, that in this region, a very peculiar shape of oxide will be created. And this is what is called, what is the name of this? I think I have pointed out earlier, somewhere, sometime. It's called Bard's beak. This is what is called Bard's beak. Anyway, today we have come to the end of the class, and what I wanted to emphasize that if you replace this silicon in the isolation region by oxide, you can eliminate the sidewall component of capacitance drastically, and that ultimately improves the cutoff frequency of this device. That means you can use it for still higher frequencies. The isolation becomes very, very effective up to very high frequency. This is what is known as, this process is called low-cost process. Low-cost means local oxidation, or sometimes also called simply oxide isolation. All bipolar and MOS ICs today are fabricated using the oxide isolation process, not junction isolation. Ordinary junction isolation does not serve the purpose. Oxide isolation is the most favored process today. And there are some other things I think I'll mention in the next class. Okay? Thank you.